In this video, I'll help you solve the ALEKS problem called Calculating the Capacity of Electron Subshells. The description of each subshell actually gives us the principal quantum number and the angular momentum quantum number as well. The principal quantum number, which is also referred to as the energy level, is just simply the numerical value at the beginning of each subshell designation. So it is just literally the number that is in each one of these subshell descriptions. The angular momentum quantum number is the quantum number that describes the shape of the orbital, and the shape of the orbital is also given to us by the letter description in each subshell. Now, the letter description is not the same thing as the quantum number, even though they both represent the same thing. So the angular momentum quantum number L is not F or S or D, and that is a little bit confusing. Each orbital description, for example, the s orbital, has a specific angular momentum quantum number value. The s orbital's quantum number L value is 0. For the p orbital, L equals 1. For the d orbital, L equals 2. And for the f orbital, L equals 3. And again, this is a little bit of a confusing topic because when it comes to describing the shape of an orbital, we could either choose to describe the shape of the orbital using the angular momentum quantum number, which is going to be a numerical value, or we could choose to describe the shape of the orbital using a letter, S, P, D, or F. They both give us the same piece of information. I'm not sure why we have two different ways of doing it. And last but not least, we are being asked to indicate the maximum number of electrons in each subshell, and that is based on the angular momentum quantum number L, or the letter value, or the letter description of each subshell. In an s orbital, the maximum number of electrons is 2. In a p orbital, it is 6. In a d orbital, it is 10. And in an f orbital, it is 14. Now, if you're having a hard time remembering the maximum number of electrons per orbital, I can show you how to count that out on the periodic table. This is going to be particularly easy, especially if you know how to read electron configurations off of a periodic table. If you do know how to read electron configurations from a periodic table, then you know that right now what I'm doing is blocking off the different areas of the periodic table that correspond to the s, p, d, and f orbitals. And so this area of the periodic table corresponds to the s orbitals, this corresponds to the p, this is the d, and these are the f orbitals. In any given row, maybe ignore the first row, in any given row on the periodic table, there are a total of 2 boxes in that row that correspond to the s orbital, and that tells us how many electrons we can have in any s orbital. In any given p orbital, in any given row, we have a total number of 6 boxes, 6 elements corresponding to a p orbital, and that tells us how many electrons we could have in a p orbital. In any given row, we have a total number of a total number of 10 elements in the d area, which tells us how many electrons we can have in a d orbital. And then last but not least, in any given row, we have a total number of 14 electrons in an f orbital.